Hello, in this video I want to teach you how to do some temperature calculations with the formula Q equals mc delta T. That triangle is a delta. I talked about it in my last video. So this is a four-part lesson. I'm going to start by talking about mass and thermal energy, the way that they relate. Then I'm going to talk about substance type and thermal energy, for example, why metals heat up so much quicker than water does. Finally, I'm going to talk about how to calculate heat transfer and then do some example problems. So let's start with part one, mass and thermal energy. And thermal energy is just the energy in heat. For example, it's not the energy of light, it's not the energy of uranium, right, nuclear energy. It's just the energy stored in heat. So let's say I have two objects and they're both at 80 degrees. I have 1 cup of water and I have the whole ocean. They're both 80 degrees. Which one has more thermal energy inside of it? If I took the energy out of the cup of water and the ocean, which one would have more? Well, they're both at the same temperature, so maybe we think they have the same amount of energy, but that's not right. The ocean has more energy. Objects at the same temperature can have different amounts of energy inside them if they have different amounts of stuff. Think about it like this. 1 cup of water is about this much of the ocean. The ocean is not just 1 cup of water, it's 2, 3, 4, several thousand, several million cups of water. So the ocean is going to clearly have several million times the amount of thermal energy that 1 cup of water has. Because if you want to imagine the ocean as just 4 billion cups of water, you could do that. So we should have 4 billion times as much thermal energy. So the takeaway is if two objects made of the same substance are at the same temperature, then the one with more mass is going to have more energy stored in it. So more massive objects will hold more energy per degree of temperature than less massive objects. The ocean at 80 degrees holds more thermal energy than a cup of water at 80 degrees. Even though they're both 80 degrees, 1 degree of the ocean matters more. So to see if you get it, which one of these would have more energy? 10 grams of water at 50 degrees Celsius or 20 grams of water at 50 degrees Celsius? Well, 20 grams of water is more water. So the more massive object is going to have more energy at the same temperature. So 20 grams of water would have more energy. Okay, that's part one. Let's go to part two, substance type and energy. Let's say I have two objects at 80 degrees, and this time let's say I have the same mass of both. I have 10 grams of water at 80 degrees, and then I have 10 grams of iron at 80 degrees. So metal and water, same temperature. Which one has more thermal energy stored inside of it? So here's a hint. They don't have the same amount, even though they're at the same temperature and they're the same mass. One of them has more than the other. Well, the water has more thermal energy inside of it. Let me explain a little, because this might seem a little weird. Let's say you have a metal pot, and it weighs 2 pounds, so you have 2 pounds of metal, and you put this pot on a stove. I don't know if you've ever put an empty pot on a stove, but it heats up very quickly. The thermal energy is going out of the fire on the stove and into the metal pot. There's energy transfer happening right here. And the metal pot heats up really quickly, so if you touch the metal after a few seconds, you will burn your hand or you burn your finger. Now, if you take that 2-pound pot and you add the same mass of water, so you add 2 pounds of water to the pot, so you're heating it up instead, and 2 pounds of water is about a liter, like a liter of soda, add that much water to the pot. So you add 2 liters of water. The stove is giving the heat energy to the water the same way it was giving it to the pot, right? You have the same rate of energy transfer. But the water heats up really, really slowly, even though it's gaining energy at the same speed the pot did. So for example, you could try this at home. You could take a pot, a metal pot, put it full of water, and then put it on your stove. It's not going to heat up forever. You can stick your hand in there and not burn yourself for several minutes at least, right? This is because every chemical will hold different amounts of energy per degree of temperature. So water takes a lot of energy to heat up by 1 degree, whereas metal takes only a little bit of energy to heat up by 1 degree. The amount of thermal energy that 1 degree can hold is called an object's heat capacity. And I'm going to use a metaphor, and I hope it helps. If the heat capacity is a high number, the substance can hold a lot of energy per degree. And if the heat capacity is a low number, then the substance can hold only a little bit of energy per degree. So imagine it like this. This is my metaphor. The stove is going to give 1,000 joules of heat energy to the pot in 10 seconds. That's true. In 10 seconds, the stove gives some energy to the pot. So 2 pounds of iron, like this pot, has a heat capacity of about 417. Don't worry about where I got that number. Don't worry about the units. This means that 1 degree of temperature for the pot, if it goes up by 1 degree, it's going to hold 417 joules of energy. Every degree is 417 joules. That's how much it can hold. So to hold these 1,000 joules of heat, well, you have the first degree, and imagine it like a person holding up a box, lifting weight instead of lifting energy. The first degree can hold a maximum of 417 joules, because that's the heat capacity of this metal. But that's not all the energy. There's still more energy. There's still 584 joules left. So the pot needs to go up another degree. So it gains another degree of temperature. And then that degree of temperature sort of holds 417 joules of energy, because it's a heat capacity. So the next 417 joules goes into heating it up by the next degree. So now collectively, the metal pot went up by 2 degrees and is holding 834 joules. But that's still not enough, because the stove gave it 1,000 joules, so it didn't go up by 2 degrees, it went up by more. So the pot has to go up another degree to hold the rest of the energy. And now this last degree, it doesn't go all the way up the degree. It's not holding its maximum capacity, it's just going up a little bit. So the iron pot, in order to hold 1,000 joules of heat, like you give it 1,000 joules of heat, it goes up by a little less than 3 degrees, 2-point-something degrees. That's how much it heats up by. In other words, the 1,000 joules of heat causes the pot to increase in temperature by about 3 degrees. Now let's look at the water. I'm going to give the same amount of energy to the water instead of the pot. So 2 pounds of water, if you do the calculation, it has a heat capacity of about 3,790. And this is about 10 times larger than the iron pot of the same mass. So that means that 1 degree of the water, when the water goes up by 1 degree, it holds 3,790 joules of energy. So if you had the water on the stove for the same amount of time, it would get 1,000 joules of energy, and if it goes into the water instead of the pot, well, the degrees of water can hold more energy than the degrees of iron. Imagine they're big, strong, instead of small and weak. So the first degree can hold up to 3,790 joules, but it doesn't even need to hold this much. I mean, I only gave it 1,000 joules. So the water doesn't even go up by 1 degree. Not even 1 full degree does the water need to hold this much energy. In other words, the 1,000 joules of heat causes the water to increase by less than 1 degree, even though the iron increases by 3 degrees. The heat capacity of a substance tells you how much energy every single degree can hold. An object with a high heat capacity can hold lots of energy in 1 single degree. And an object with a low heat capacity can only hold a little bit of energy per degree of temperature. So if you have one chemical with a low heat capacity and another one with a high heat capacity, for example, 1 gram of iron with a low heat capacity of about 1/2, and 1 gram of water with a high heat capacity of 4, these are different numbers because I have less of them, 1 gram instead of 2 pounds. And I give both of these objects the same amount of heat energy, so I give them 8 joules. Let's say I give the iron 8 joules of energy. Every single degree can only hold 1/2 of a joule. So to hold 8 joules, I'm going to need 16 degrees. So if I add 8 joules of energy to 1 gram of iron, it goes up by 16 degrees. Because the degrees are like weak, if you want to think of it like that. Now the degrees of water are strong. So to hold 8 joules of energy, I don't need all these degrees. I don't need 16 of them. Every degree of water is strong. It holds a lot of energy, and so I only need 2 degrees. The units for heat capacity are joules per degree. How much energy can every degree store? We normally talk about the heat capacity of just 1 gram of a chemical, though, which is called the specific heat capacity, and the units are joules per gram per degree. But don't worry too much about the units. You can ignore them. You should think of heat capacity as the amount of energy that 1 degree holds.